Okay, so how does a transporter which facilitates diffusion work? Explanation of transporter mechanism using Ka. If there is a high concentration of ligand on the extracellular side than the cytosolic side, then there will be more transporters with bound ligand when the transporters are open to the extracellular side than the intracellular side. The opposite is true if the concentration gradient is flipped. So let's look at this piece by piece. Let's create a situation, right? I have a situation, and here's my membrane. And let's say that I have X amount of my solute that I'm interested in inside. So concentration inside is X amount, and concentration outside is, let's say, 10 times more. Okay? Now, X could be any positive number, right? And I have my transporters. Now, I'm not going to draw the whole thing, but let's just say open on the outside, open on the facing the inside, and occluded. Okay, occluded is the square, right? Again, imagining that when we're talking about a transporter, we're not talking about a single molecule of transporter. There's going to be a certain number of these transporters on the cell membrane, so the cell membrane will have a certain concentration of these transporters on it, right? So when we're looking at the Ka, right, the Ka for transporter binding its ligand. So we have this equation, transporter plus ligand, giving me transporter ligand. This is the binding equation. So I have concentration of transporter ligand, concentration of transporter times concentration of ligand. And this Ka is unique to this transporter. It's just the affinity of the ligand to the transporter's binding site, right? So we can easily just say concentration outside would be concentration of ligand outside and concentration of ligand inside. Now, when a bunch of these transporters are open to the outside, that is a different concentration of ligand. So if open to the outside, the Ka would be transporter times ligand, which is ligand outside, right? Over transporter ligand. And we're going to leave this L here without a designation of O and I because we're just going to have it as bound, right? We just leave it like that for now. And for the Ka for the transporter facing the inside solution being open to the inside solution, we have transporter, ligand inside, and transporter ligand, right? Now, if I say ligand concentration is X for this right here, right? Well, ligand outside is 10 times more, so I'll be multiplying this number by 10, right? And replacing the O with an I. And if I do that, well, if the Ka for this is some number, then the Ka for here simply has to be this times 10, right? So if the transporters open up to the outside, it's 10 times more likely to have more ligand bind to transporter, whereas it's open to the inside, then it's 10 times less likely to have transporter ligand complexes. So you can imagine that if I somehow was magically able to make all this transporter, all of them open up to the outside, well, it's going to pick up a bunch of ligand, right? And then it's going to, let's say I magically are now able to make it go to the occluded state and then open up to the inside. Well, now it has 10 times too much transporter ligand, and it must release some of that ligand to get back to Ka. Now, of course, that magical scenario is not happening, but the fact that you're more likely to have transporter ligand when facing the higher concentration side than the lower concentration side is enough to ensure that this transporter, even though it's flipping to these 3 states randomly, that it will facilitate diffusion. This is a bit of a more difficult way to look at this, but if you just think about it for a second, is that you have 2 concentrations of ligands on 2 separate sides, and the binding pocket is only exposed to one side at a time, and that if it's exposed to one side, if you have a higher concentration of ligand, you're more likely to pick up the ligand, and you're open up to the lower concentration side, you're more likely to release it than to pick it up again. Okay, so in this scenario, when you're opening up on the low concentration side, like here, you're less likely to pick it up, and then you could flip to the occluded state empty-handed, and then go to opening up on this side, because if you go back to being open to the low concentration side, if that happens, it's like nothing happened, right? Nothing has happened. If it then goes to open to the other side empty-handed, well, it's very much more likely to pick up a ligand and then go back to the occluded state. But if it then goes and opens up to the other side, well, it's more likely to release the ligand because you have a lower concentration of ligand on that side. Okay? Now, using a different way to look at it is this. Now, before doing that, we're going to talk about enzymes again. Now, what does an enzyme do? An enzyme, it speeds up a process that will typically not happen by itself, meaning the process is favored to happen, right? A spontaneous process, at least the enzymes that we're talking about with the Michelson-Menten equation of V equals to V max over substrate concentration plus Km, right? These were reactions that are very favorable. What does an enzyme do? An enzyme will make a process that is supposed to happen, but is happening so slowly that's like it's not even happening, and speeds it up. So it increases the rate, right? What is another property of enzymes? Enzymes bind their substrate, right? So they bind their substrate. Now, a transporter is speeding up a rate of a spontaneous process, diffusion, many folds. Glucose is not going to cross the cell membrane without glucose transporters. Also, a transporter must bind its ligand to do its work, to speed up the rate of this physical reaction, which is the movement of molecules down their gradient. So we can use these properties, this equation, for transporters and model the movement of molecules across a membrane by a transporter that moves one ligand only. Okay, that's very important. One ligand only. Okay, not 2 or 3 or 4, because this equation for enzymes, the reaction that it's modeling is a reaction where you have a single substrate, right? Not 2 substrates or more. So that's basically what is being said here. Explanation of transporter mechanism using the Michaelis-Menten equation. The movement of a transporter's ligand in one direction is similar to a very favorable reaction being catalyzed by an enzyme. Since we're looking at transport in one direction, i.e. extracellular to cytosol, or the opposite direction, it is akin to a very favorable reaction where the rate of the reverse reaction can be ignored. So what does this mean? Meaning that if we simply look at the rate which a transporter is moving something from the outside to the inside, and then oppositely look at it separately as it's moving things from inside to outside, we can use the Michaelis-Menten equation, because in both cases we're ignoring the reverse. We're simply saying we're going to use this equation to look at movement in one direction, then we're going to use the equation to look at movement in another direction and get the velocity, the rate of movement of that molecule. Okay? The transporter must bind its ligand the same way an enzyme must bind its substrate. Just like an enzyme-catalyzed reaction, there are a limited number of transporters on the membrane and therefore a limited number of ligand binding sites. Thus, saturation can occur. This is just saying that just like an enzyme-catalyzed reaction where you had V and substrate concentration, you had a Vmax, right? Here's my Vmax. And it went like this, where it got saturated, right? Because you have a limited number of binding sites, or in the case of enzyme, active sites. The membrane is akin to the energy of activation barrier, a barrier that must be overcome in order for a favorable process to move towards equilibrium. So what is a transporter doing? It's taking an impermeable membrane and making it permeable to that molecule, right? So you can think of the cell membrane as being an energy activation barrier. Therefore, diffusion of a transporter's ligand by a transporter can be modeled using the Michaelis-Menten equation, where V outside, or VO, to N is the rate by which a ligand is moved from extracellular to the cytosolic side, where VI to O, the rate by which a ligand is moved from the cytosol to the extracellular side. Vmax is the maximum rate the transporter can achieve and is concentration dependent. The higher the concentration of transporter on the membrane, the higher the Vmax. This is the same thing as enzymes. Remember, the Vmax was dependent on the concentration of enzyme. So the Vmax for a transporter is going to increase the more transporters there are on the membrane. Km is the concentration of ligand needed to reach half a Vmax. Same as enzymes. CO is the extracellular concentration of ligand, and Ci is the cytosolic concentration of ligand. So for the movement of ligand from outside, extracellular to inside, we have VO to I equals the Vmax CO over Km plus CO. So in this case, you can see the concentrations are just concentration outside. When we're looking at outside to in, and the case of inside to out, you're just simply changing the concentration to the concentration of the ligand that is inside in the cytosol, right? Right there. We will define the rate of outside to in as positive and the rate from inside to out as negative. And this is just because the two rates are completely opposite each other. So if one is positive, the other one is negative. So we're just simply setting up a rule where outside to in is a positive number and the VI to O, inside to outside, is going to be a negative number. And then we add them up, right? Or you can simply, if this is something you don't want to think about, you can simply change this to a minus. But you have to remember that inside to outside is going to be the one you're subtracting by, right? And that will give you the total rate of movement, okay? The movement of ligand across the membrane can be depicted as such. So let's actually look at what this will look like. So here is the plot that we had for an enzyme, but we're going to change it for a transporter. Nothing much is going to change. We have velocity. We have a Vmax. We have a half a Vmax, which would be about right here. And we have our ligand concentration, so this would be ligand concentration. And we have our plot, just as before. Now, when we're looking at this, for example, let's say I have a system like this. I have, here's my membrane, and I have CO and Ci. And before we carry on, let's look at our Km. Here's our Km. And by the way, Km has the same special type of meaning as the Km for an enzyme does. It gives you an idea of the affinity of the ligand for the binding pocket of the transporter. Okay? So we can just say that, okay, the concentration outside equals to, let's say, 2 km. And the concentration equals to 1 half km. So obviously, this is a molecule that we're not really worried about. It doesn't have a charge, so we're not worried about the potential gradient or anything like that. We're just worried about the concentration gradient in this case. We're not going to use this equation or this whole thing for anything that has a charge on it, because then we have to worry about the potential gradient also. Now when we're looking at this, well, concentration outside is higher than concentration inside, so we expect the concentration gradient to be pointing in this direction, so things should diffuse from outside to in. So what does this look like? Well, we said concentration outside is 2 km, so it'll be somewhere around here, right? This is about 2 km. So this will go to my plot here. Here's my V from outside to in. Now what about the inside to out? Well, concentration inside was half a km, so this is about half a km. And this will go here, and this would be my VI to out. Now VI to V, that would be my V in to out, I'm sorry. So my VO to I is bigger than my VI to O. So when I go ahead and say V equals to VO to I minus VI to O, I will get a positive number, right? So this is bigger than 0. So bigger than 0 means things are moving from outside to inside. The larger this number, meaning the more positive it is, the bigger it is, that means the rate is higher, right? And that's basically it, right? This gives you an idea by using the equation that modeled very favorable enzymatic reactions and using it for transporters. And that's how a transporter works. It's a good way to model it. Alright, so we'll stop this video here and we'll go over these examples in the next video. Okay guys, thank you. Bye-bye.